Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate in the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now I'm just going to get started on our set of questions for today's session. Okay, so the first question asks, what is the difference between the endpoint and equivalence point in a titration? Okay, so I'm just going to make a comparison chart. Of endpoint versus equivalence point. Okay, so basically the endpoint in a titration is when your indicator changes color. And that's if you have like a color changing indicator. There are other indicators such as like the voltage, but commonly the indicators tend to change color, so I'm just going to write that down. The equivalence point, on the other hand, is when your titrant is chemically equivalent to your analyte. Okay, so another point about endpoints is that weak acids have only one. However, with equivalence points, weak acids can have multiples. Okay, so let's check out the answer from our junior tutor. In a titration, the equivalence point corresponds to the theoretical completion of the reaction, while the endpoint is related to the experimental completion of the reaction determined by an indicator or an instrument. That was a great answer. Equivalence point is the point or concentration of added titrant which is stoichiometrically equal to the amount of moles of analyte in given sample. For this reason, the equivalence point is often called the stoichiometric point. Endpoint, as the name suggests, the endpoint is related to the end of the titration. For the accuracy of the titration to be high, the endpoint should be as close to the equivalence point as possible. The difference between the equivalence point and endpoint is referred to as indicator error. That was a great answer, so this solution is correct. Okay, so let's move on to question number 2. Which of the following compounds will behave least like an ideal gas at low temperatures? So we have H2, SO2, chlorine, helium, and nitrogen. So even just looking at the different compounds that they give us, you'll notice that like H2 and F2, these are the smaller diatomic molecules. And even just helium is an inert gas. And same with nitrogen. And basically our SO2 compound is the only one that has two different elements in it. And it's also the largest molecule. So therefore, I would say that the SO2 is not likely to behave as an ideal gas. Let's check out the answer from our junior tutor. Hydrogen is the smallest molecule, and due to this, it will certainly act ideally. SO2 is a larger molecule with specific geometry, therefore it is not likely to behave ideally. Yep. F2 is also quite small. I would expect it to behave semi-ideally. Helium is an inert gas. Nitrogen is very inert due to its strong bond between the nitrogens, therefore it will act ideally. From these statements, SO2 is the least likely to behave as an ideal gas. So this solution is correct. Okay, so let's move on to question number 3. Write the net ionic equation for the equilibrium that is established when ammonium iodide is dissolved in water. Okay, so first, let's write the dissolution of ammonium iodide. Okay, so this is the chemical equation for ammonium iodide plus water. We'll make NH3 plus H3O plus iodide. So now I'm going to write out the ionic equation. So if we were to write ammonium iodide separated into its ions, it would be NH4 plus I minus. Since this water is a liquid, I'm not going to write it in an ionic form. And then this side stays the same. So now I'm just going to cross out my spectator ions. So spectator ions are ions that appear on both sides of the equation. So the only spectator ion here is the iodide. And then I'm going to write my net equation. Which is that. So because we have H3O+, this indicates that our solution will be more acidic. Okay, and you do something similar with the ammonium bromide. So I'm just gonna, yeah, sure, I'll do part B as well. So part B says to write the net ionic equation for the equilibrium that is established when ammonium bromide is dissolved in water. So something similar takes place. We have ammonium bromide plus H2O. And then I'm going to write out the ionic equation. So the water stays the same. And I'm going to cross out my spectator ions, which is just the bromine in this case. Then I'm going to write out my net ionic equation. Okay, so again, we have H3O+. So this solution will be acidic. Okay, so let's look over to what our junior tutor said. They wrote out the dissolution of ammonium iodide. They have the net ionic equation here. They removed the spectator ions to get NH4+, H2O, NH3, and H3O+. You'll have an acidic solution. And then they do the same thing for ammonium bromide. And again, the solution is acidic. So this solution is correct. Okay, so on to question number 4. Which of the following is a reasonable criticism of the Bohr model of the atom? A. It makes no attempt to explain why the negative electron does not eventually fall into the nucleus. So that isn't the option. Since it does do that. The next one is it shows the electrons to exist outside the nucleus. does not adequately predict the ionization energy of the first energy level electrons for one electron species for elements other than hydrogen. So the Bohr model does that as well, so that isn't our option. D, it does not adequately predict the line spectrum of hydrogen. So that is not true as well. So let's check out our last option. It does not adequately predict the ionization energy of the valence electrons for elements other than hydrogen. So this is a reasonable criticism. So the answer is E. Okay, so I'm gonna draw out an example of like an element that has a lot of valence electrons. So let's call it like element X. Here to draw out its diagram. You can have 8 here. And then if I draw out another one, another of electrons. The Bohr model does not take into account the screening effect. In multi-electron species. Okay, so let's see the answer from our junior tutor. They also selected E. It doesn't adequately predict the ionization energy of the valence electrons for other elements other than hydrogen, as he did his calculation for only one electron species. For multi-electron species, there will be some screening effect of other electrons, I think. That's what it says, which he didn't consider. We want to take out, let's say we want to take out this electron, which is on the inside. The 1, 2, 3, 4, 5 electrons will have some screening effect. Bohr only did his calculation for one electron species, not for other multi-electron species, as he did not say anything about screening and the role of other electrons. Okay, so this solution is correct. And now we can check out question number 5. It's kind of blurry, but basically they have different Fisher projections of some aldopentoses shown below, with options ranging from A to F. So which structure is the enantiomer of D arabinose? Okay, so This is question number 5. So before I go through all of the different Fisher projections, first I'm just going to write down the diarabinose. So they have an alcohol on the left, and then 2 alcohols on the right. And basically the definition of an enantiomer is that it is the mirror image of original structure. I'm just gonna draw like an imaginary mirror using this dotted line. And then I'm going to draw out the enantiomer of diarabinose. So this top part stays the same along with the bottom part. But now I'm going to write these in their mirror formed. So now the first alcohol is on the right. The second alcohol is on the left. And then the last alcohol is also on the left. And then the name of this enantiomer is L-arabinose. Okay, so let's see the answer from our junior tutor. Oh yeah, I didn't even look at the options. So let's see the options here. Okay, so this is option number C. Okay, now let's look at the answer from our junior tutor. Okay, so they also pick C, L-arabinose. And then I'm going to say this solution is correct. And then also just add definition of the enantiomer and how we got this answer. Okay, so the solution is correct. Enantiomers are the mirror image of the original structure. Okay, so this solution is correct. Okay, so let's check out question number 6. How many valence electrons are in an atom of chlorine? So I'm going to draw chlorine right there. And I'm going to write out the total electrons in chlorine is equal to 17. So I'm going to draw out the electron dot diagram. So this inner ring has 2 electrons. This one will have 8. So that is 10 in total. So I'm going to need one more ring of electrons. and I need to count out 7 more. So 1, 2, 3, 4, 5, 6, 7. And then when we say valence electrons, they are the electrons in the outermost shell. So therefore, there are 7 valence electrons in the chlorine atom. That's a pretty simple question. Let's look at the answer from our junior tutor. Concept. The distribution of electrons in different orbitals is called electron configuration. The electrons filled in the outermost shell, or the electrons present in the highest principal energy level, are called valence electrons. The filling of electrons in different energy levels or orbitals is done in accordance to Aufbau principle. It states that electrons are filled in the orbitals in order of increasing energy of the orbitals. The increasing order of energy of the orbitals is as follows. And then they just have the example there. Step 1. The atomic number of chlorine is 17. The number of electrons in chlorine is 17. And the electronic configuration of chlorine is as follows. So they didn't write it down, but I know what they mean. Step 2, the highest principal energy level is 3. The electrons present in 3s and 3p orbital are valence electrons. Distribution of electrons in different orbitals in chlorine atom is shown as... And then they kind of wrote it this way, which I would say is more accurate. Therefore, the number of valence electrons in atom of chlorine is 7. Oh, and then they have similar problems. So this is what the distribution of electrons would look like in a carbon atom. And then you count out 4. They have it for oxygen, which is 6. So this solution was very well written. It is correct. Okay, so now let's move on to question number 7. So it is a 2-part question. The first part asks, you need 2.5 moles of iron for an experiment. How many grams of iron must you measure out? So I'm going to write down what we know. We know the number of moles of iron is equal to 2.5 moles. And it's not given, but we can look it up on a periodic table. But the molar mass of iron is equal to 55.845 grams per mole. And the equation that we need to use to solve this in order to find the mass of iron in grams is actually pretty simple. You would just use the equation M equals the number of moles times the molar mass. Okay, so let me write down these values. So all we have to do is multiply 2.5 moles by the molar mass of iron. Then we get a final answer of 139.6 grams of iron. Okay, so now let's check out the second part of this question. How many argon atoms are there in 1.5 times, I'm assuming that's 10, like times 10 to the power of 2 grams of argon. So again, we are going to write down everything that we know. So the mass of argon is 1.5 times 10 to the 2 grams. I'm also going to write down the molar mass of argon, which again you can just find in a periodic table. And it is 39.948 grams per mole. And the first thing we want to do first is find the number of moles. And that is because when we use Avogadro's, that is because we want to use Avogadro's number to find out the atoms. So every time you have like atoms or particles or photons, and we need to calculate how many particles there are, we're going to use Avogadro's number. And the value for it is 6.023 times 10 to the 23 atoms per mole. Okay, so today is actually October 23, so people call today Avogadro's number day. So that's kind of cool. Not like cool, but anyways, so the first thing we're going to do is calculate the number of moles of argon. So to do that, it's going to be mass over molar mass. So it is 1.5 times 10 to the 2 grams over 39.948 grams per mole. If you ever get confused about which M is on top, just try to look at the units. So your grams should cancel out. And then your moles should go from the denominator to the numerator. So this gives us a final mole value of 3.75 moles. And then that's A. To find the number of atoms, we are going to take our value for the moles and then multiply by Avogadro's number. And again, you'll notice the units canceling out. So our moles should cancel out, and we are left with the number of atoms. So in this case, it'll be 2.26 times 10 to the 24 atoms. Okay, so let's see the answer from our junior tutor. Part A, we know that the moles equals mass over atomic weight of iron. Mass of iron equals moles times atomic weight, and they end up with 139.5, so there's just some rounding differences, but it's pretty much the same thing. Part 2, we know that the atomic weight of argon is equal to 40 grams per mole. So moles in 1.5 times 10 to the 2 grams of argon will be 1.5 times 10 to the 2 divided by 40, which is equal to 3.75 moles. Now there are 6.023 times 10 to the 23 atoms in 1 mole. So the number of atoms in 3.75 moles is 22. They got, oh, okay, I see. So they got the same thing, except they did it to 10 to the power of 23, but it is the same answer that I got as well. So this solution is correct. Okay, so let's check out question number 8. Classify each of the characteristics as lock and key model or induced fit model or both. 1. Active site is rigid. 2. Enzyme is substrate specific. 3. Substrate shape is modified. 4. Active site is flexible. 5. Enzyme returns to initial shape after catalysis. And 6. Active site substrate interaction induces an optimal fit for catalysis. Okay, so first I'm just going to give a definition of both models. So for the lock and key, this is when your substrate perfectly fits your enzyme. And your enzyme doesn't change. So that makes sense, because that's how a lock and key works. And then on the other hand, with induced fit model, this is when your enzyme will change to either join your substrate or break it down. Okay, so now I'm just going to make 3 columns. The first is the lock and key model, induced fit, then both. Okay, so let's look at option 1. Active site is rigid. So basically that means that the active site can't, it's not easy for it to change its shape. So this is an example of a characteristic of the lock and key model. So 1 goes there. Okay, so let's look at 2. The enzyme is substrate specific, so this can be both of them. Okay, so now let's look at 3. The substrate shape is modified, so we know that this is induced fit. For active site is flexible, again, we know this as induced fit. Five, enzyme returns to initial shape after catalysis. So this is actually a characteristic of both of them. Since even for lock and keys, since it doesn't change anyways, so it is its initial shape. And then lastly, 6, active site substrate interaction induces an optimal fit for catalysis. So this is the example of induced fit model. Even the word induces is in the sentence. So pretty straightforward question. Let's see the answer from our junior tutor. Lock and key, active site is rigid. Induced fit model, active site is flexible. Active site substrate interaction induces an optimal fit for catalysis. And substrate shape is modified. And then for both of them, enzyme is substrate specific and enzyme returns to its initial state after catalysis. So this solution is correct. Okay, so now let's check out question number 9. A helium nucleus has 2 protons and 2 neutrons. How many electrons does it take to equal the mass of a helium nucleus? So this is question number 9. Okay, so I'm just going to write down the values of the masses of protons, neutrons, and electrons. Okay, so if you compare these 3 masses, you'll notice that the mass of the proton and neutron are practically the same value. And on the other hand, your mass of electron is way smaller. So what makes every element unique is that they all have different numbers of protons. So in the case of helium, The question says it has 2 protons and 2 neutrons. So let's calculate the mass of a helium nucleus. I'm just gonna write mass of helium nucleus, and then I'm just going to take our different masses of protons and neutrons and then multiply it by 2. So even though they're the same value, I'm just going to separate the 2 just because it's good practice. Okay, so then when we simplify this, it's the same thing as writing 2 times 3.35 times 10 to the negative 27 kilograms. Then we can calculate the mass of our helium nucleus to be 6.69 times 10 to the negative 27 kilograms. Okay, so now for the part of the question, how many electrons does it take to equal the mass of a helium nucleus? So we can have X, so what we're looking for, is equal to the helium nucleus mass over the mass of 1 electron. Okay, so subbing these values in, I'm going to put the 6.69 times 10 to the negative 27 that we just calculated, all divided by the mass of 1 electron, which is the 9.1 times 10 to the negative 31 kilograms. And then when we calculate this, we end up with a value of 7.4 times 10 to the 3 electrons. Okay, so let's see the answer from our junior tutor. To determine, calculate the number of electrons required to create mass equal to the mass of a helium nucleus. Answer, the number of the electrons required to create mass equal to the mass of a helium nucleus is... there's no actual values in the question. But it looks like they're talking us through how to answer it. Maybe they just didn't have the values of the masses of protons, neutrons, and electrons. So I'm just going to write it down. So bear with me. I had to type this all out. Okay, so I said that given that the mass of proton is equal this, the mass of a neutron is that, and the mass of the electron is the 9.1 times 10 to the negative 31. For helium, the mass of the nucleus is 2 times 1.67 times 10 to the negative 27 plus the same thing. And we get the mass of the nucleus. For number of electrons, it is, I think I'm double checking this. .69 times 10 to the negative 27 kilograms divided by 9.1 times 10 to the negative 31 kilograms. Then we get X equals 7.4 times 10 to the 3 electrons. Okay, so even though the junior tutor gave us how to answer it, it was kind of confusing to read and didn't really add any of the actual values. So I'm just going to say that this solution was incorrect. Okay, so I think we have time for one more question. And this is question number 10. Name the following alkyl halides according to the Iupac rules. So first, let's just write down compound A. Okay, so the first thing I want to do is I want to circle the parent chain. So the parent chain is the longest chain of carbons that contain the most important things. And now I want to number them. So I want the lowest number possible when I write down my name. So since most of my substituents are on the first couple carbons, I'm going to start the numbering from here. So 1, 2, 3, 4, 5, 6, 7. And now I want to look at all my different substituents. We have a methyl group here and here. And then we have 2 bromine groups here. And those are the prefixes we would use. So putting it all together in alphabetical order, I'm going to do bromo first. So on carbons 3 and 4 are the 2 bromines. So it's going to be 3,4 dibromo to indicate that there is 2 of them. 2,6 dimethyl, since there's 2 methyls. And then because our parent chain has 7 carbons, it is going to be heptane. Okay, so let's look at B. Now we have a double bond here. And then an iodine at the top. I'm going to circle my parent, which is this long chain. And then I'm going to number it from the bottom out. And that's because, again, I want the lowest number of carbons. And then just to show where our substituents are, it is going to be 2 iodo for the iodine. Hex, because there's 6 carbons in the parent chain. 4 ene to show where our double bond is. Okay, so now let's look at C. Okay, so we have a bromine group and a methyl group here, a chlorine group up there, and then another methyl group there. So let's circle our parent chain. And then to number them, I'm going to start from here, since I want carbon 2 to have the majority of the substituents. And then when I'm naming this, I'm going to do my bromine first, since it is in alphabetical order. So it's 2 bromo, and then the chlorine, 5 chloro. Let me continue here. And then 2, 6 to show where our methyl groups are. Dimethyl heptane. Then let's quickly do the last one. And then we have it kind of sticking up like that. So when we circle our chain of most important things, I'm not going to go all the way to the left. I'm going to be circling this part as part of the parent chain. And now to number it, the one with the bromine, I'm going to label as carbon 1, 2, 3, 4, 5, 6. So try not to get confused when you write out your parent chain, because they try to trick you in writing it like horizontal like that, but basically this would be our parent chain. And then to name this, it would be the 1 bromo, because the bromine is on the first carbon. And now 2 methyl, hexane, because there are 6 carbons. So let's see the answer from our junior tutor. They got 3,4-dibromo-2,6-dimethyl-heptane. They numbered it this way and got 5 iodohex-2-ene. But since we want the lowest number possible, I would label this carbon as carbon 1. So I'm going to rewrite that later. But for C, they also got 2 bromo 5 chloro 2,6-dimethylheptane. And then here they labeled it 1 to 6 going left to right, which is not what I did. But they got 3 bromomethylhexane. So I'm just going to rewrite for B and D. So B can be 2 iodo X4-ene if we want the lowest number in our name. Also, D can be 1 bromo 2 methyl hexane. So their answer was still correct. Like, it's not wrong. And there are different ways you can name these. So I'm going to say the solution is still correct, but I still added what I would name them. So solution is still correct. So that is all the time we have for today. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, then please hit the subscribe and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And if you liked today's video, then go ahead and give it a thumbs up and leave a comment. And don't forget to share it with all of your friends and classmates if they needed help with chemistry. So this has been Donna from OneClass, and I hope to see you soon. Bye.